All right, so this section is 4.3. I'm going to break it up into two parts again because it does cover a lot. Basically, what it talks about is intervals on which a function is increasing, decreasing, extrema, concavity, something else called inflection points, and we're going to get to all that. So there are a lot of notes. This has been posted on Canvas. It'll be under the files tab. I also have a link for it next to the video. So you can go ahead and print this out and follow along because as you can see, it's just a lot of little definitions and terminology. So this is going to help us get, a little bit more quickly into the problems. But what do we mean by increasing and decreasing this concavity stuff? Like conceptually, this is what we have. Let's say we just have a random graph, right? And it's doing something like this right here, just something random like that. And we're asked about where is this thing increasing and decreasing and all this stuff like that. Remember, increasing and decreasing is just basically where you have a positive slope for increasing or a negative slope for decreasing. So, you read a graph from left to right. So we know, oh, we're going up the hill, correct? So you'd be increasing right there. You would also be increasing along this interval as well. And likewise, we're also decreasing in this particular curve, right? If we go from left to right, we're going down the hill. Same thing right here. And I'm just going to label this. This will be like point A, this is B, and this is C right here. So let's say, for example, and this goes back to Math 130, you were asked about increasing and decreasing, right? Like we had intervals on which something is increasing, and this is just a review right here. If they were asking you the intervals on which this particular curve is increasing, remember it's increasing, decreasing intervals are always done with respect to x, okay, not y values. So as far as increasing, we have a couple little regions, right? You always start with the smallest region or the ones with the smaller numbers. So we got to start with this first region right here. How do we represent this chunk in terms of increasing? What do we do? Well, you ask yourself, where do you begin to increase from with respect to x? So this graph goes forever, to the left. What's way off forever to the left with respect to x? Negative infinity. So starting at x equals negative infinity, all the way until which x value are you increasing? A. So x value, don't try to find out what the y value is and say, oh, it's whatever this number is right here. No, x value. So from negative infinity to a, x equals negative infinity to x equals a, you're going up the hill. Now remember, with your intervals of increasing and decreasing, you always put parentheses. If you have multiple intervals, like what we have right here, right, of increasing and decreasing, you just put the next one, the next biggest interval. So where's the next x value that you start to increase at? B. So again, with parentheses, until what x value? Until C, right? Like that. So those are your intervals in which you're increasing. What about the decreasing? Remember, with respect to x. So what's the x value that you start to decrease at? Well, look, we're going down the hill here. What's that value? X value, A. Again, parentheses around these all the time. And until what x value do you decrease until? B, right here. Then again, you also start to decrease at where? C. Until what x value? Well, this not only goes down forever, but more importantly, goes to the right forever. But don't say you decrease until negative infinity. No, you're describing the y value. It's with respect to x. I'm not going to say with respect to x anymore. Y'all got to remember that, right? So from C to infinity, that's where you are decreasing. So that's what we mean by, intervals on which a function's increasing and decreasing. Now, how does this pertain to calculus 1, right? Well, we're going to be given an equation and not a graph, and we're going to be asked, where does this thing increase and decrease at and stuff like that. So we could graph it, right? But what's a lot easier and a lot more exact is to take its derivatives. Remember, derivative is just fancy word for the slope. So if you have a positive slope, it's increasing. A negative slope, it's decreasing. These humps right here, this, where the slope changes from positive to negative or negative to positive. Those are called critical points right there, right? Critical points. I'll just put CP. CP for critical point right here. That's where the slope transitions from positive to negative or negative to positive, or basically where the slope is 0, right? Remember when it flatlines, if you have a flat line, what's the slope of a flat line? 0. So that's 0, slope of 0, slope of 0 right there. That's what we mean by a critical number. So if you notice on the notes right here, again, this is on Canvas, right? Increasing, it says if the derivative is greater than 0 on some interval, then f is increasing on the interval. That would be like this chunk right here. Likewise, if the derivative is less than 0, meaning you have a negative derivative, then it would be decreasing on that interval. The point at which it transitions, right, from a positive to a negative slope or negative to a positive slope, those are called critical numbers. Remember, we talked about this briefly in 4.1. A critical number is what? It's where the derivative is 0 or the derivative does not exist, right? It's undefined. Now, you can have, remember we talked about briefly, we're going to get into this in a second, how to test for the intervals on which it's increasing and decreasing, but we can have local max or min values. Remember, we kind of talked about this when we were talking about the absolute max and the absolute min from 4.1. Local just means within the snapshot that you're given right there. Like in this instance right here, this would be like the local max, right? Point C would be the local max if we were asked for it, because it's the point that produces the highest Y value. Or like point B would be the local min, because that produces the lowest Y value within this hump region right here. So let's go out there and let's see, how do we test this, right? Like let's actually work a problem, right? So for these problems right here, what we want to find is the critical points, find critical points, intervals where it's increasing and decreasing. And local extrema if it does exist, okay? So these are coming right from here. See that? Again, on that handout. So how do we find out the critical points? That we did in 4.1, right? That was just to set the derivative to 0, solve for x. So CP, right? We have to find f prime of x. What is that right here? That's 3x squared minus 10x minus 8. And then we set that to 0. Then how do you solve it? You can factor it. All right. So now we have x equals negative 2/3 and x equals 4. Okay, so these are our critical points, right? So we're done with the first part right there. But now we need to figure out, where is this thing increasing and decreasing from, right? Because that's what we were also asked for. How do we do that? Well, we're going to make a number line, right? We're going to, you kind of did this in 130 right here. So how to find out where a function is increasing and decreasing? Using those critical points, they're going to serve as boundaries, okay? And we're going to choose test values within these three regions. Now, remember, we can choose any number within this region, okay? Like any number less than -2/3 will work in region 1. Like I could test -1, -2, -3, -50,000. It does not matter. And what you want to do is you want to plug that number into the derivative, and you want to see, do you want it with a positive result or a negative result? We don't care about what the actual value of the number is, just whether it's positive or negative. So let's test x equals -1. And I'll also test another number in region 1 as well to show you that it does not make a difference. You will still arrive to the same conclusion. Now, again, when you choose this test value, what you want to do is plug it into the derivative, not the original equation. You can plug into the original derivative or the factored form. Usually the factored form is easier to work with. So like this thing right here. If I test -1, we get 3 times -1 plus 2 and -1 minus 4. And again, we're just trying to see, do we have a negative number or a positive number in the end? This is -3 plus 2. That's -1. And this is -5. So you wind up with +5. So what does that tell us? That should tell us that anywhere to the left of x equals -2/3, our line would be going up. We'd have a positive slope. Now, what if I tested like x equals -4, right? Because that's also in region 1. It is a number less than -2/3. We should still get a positive result. We're not going to get 5. We don't care about that. We just care about it should come out to be positive. So if we do that, we get -12 plus 10. Plus 2 is -10. And then -8. And then you get +80. So again, that's positive right there. That's why I said it does not make a difference what number you choose within a certain region. We should all come up to the same conclusion. We could all choose a different number in either three of these regions, and we should all get positive or negative, depending on what it is. You only need to test one number, okay? If you want, you can test others in that region to double check yourself. Now, we need to test something in the second region. You could test 0, 1, 2, 3. You could test 3.999, right? Because that still lies within the second region. But the easiest is 0, right? Yeah. So this is 3 times 0 plus 2. 0 minus 4. Well, you get 2 times -4. Positive times a negative is a negative, right? Again, you just care about the sign. It's negative. So we know that in the second region, it's decreasing, or your line would be going down. Now we need a number bigger than 4 for the third region. You could test 5, 6, 7, 8, 9, 10, whatever, any number bigger than 4. I'll just test x equals 6. If you want on your paper, you can test 5. We should still come out to the same conclusion of positive or negative. So I have 3 times 6 plus 2. 6 minus 4. And you see you get a positive, right? This is 20 times 2. What if I didn't know 20 times 2 is 40? It doesn't matter. You just go, oh, positive times positive. That's a positive, right? So you can say the 40, but what matters is the sign, right? That's all you care about. Positive times positive is positive. So we know we have a positive slope from x equals 4 to positive infinity. Now that we have that, we can actually figure out the intervals where it's increasing and decreasing. So remember, this is always with respect to x, and it's wherever you have, for increasing, it's wherever you have the plus signs. So remember, this is going off forever to the left towards negative infinity. X equals negative infinity. So starting at negative infinity to negative 2/3, we're increasing. We also have this other region, right? The next one, the next biggest region, starting at 4 to positive infinity. Because again, this shoots off forever to the right towards positive infinity. Remember, you're always going to have parentheses around these values. Where are we decreasing at? What's the interval? Well, you have some minus signs, right? What's that region? Negative 2/3 to 4. So these are the intervals where it's increasing and decreasing. Sometimes you can have purely decreasing or increasing. It may not always alternate, like be plus, minus, or whatever. It could be plus, minus, minus. It just depends on what your curve is doing. So we have that. Now we need to figure out local extrema, right? Like, where's the local max or min point? How do we do that right there? So if we come back to the notes, if we look right here at the bottom, it says first derivative test for local extrema. Remember, extrema just means maximum or minimum. A function f has a local extrema at those critical points where the derivative sign changes. So basically, if you go from plus to minus, see the first one, if the derivative changes from positive to negative, then you have a local max. If the derivative changes from negative to positive, then you have a local minimum. So why is that? Well, let's think about it, right? Look, positive slope, negative slope. So positive slope means you're going up. And then at x equals negative 2/3, the hump would go down. Now with this one at x equals 4, that other critical point, what are you doing to the left of it? You're going down because the slope's negative. But what happens when you cross x equals 4? You're going up. Why? Because the slope went to positive. So if you have a hump that opens down, what does that have to be? This point must be a local max. If your hump is opening up, then this specific x value must be a local min. So we have a local max at x equals negative 2/3, and we have a local min at x equals 4, but we want these as a point, okay? You want these as a point right here. So you need to substitute these values into your original function. So remember, we started with f of x equals what? So we need to plug both of these x values back into the original equation to get out the y value where these local extrema occur at. So you can just throw that into your calculator. And you should wind up with 76 over 27. So this is a point would be negative 2/3, 76 over 27. So no decimals, okay? This is what you would enter into WebAssign, because if they're asking for the point, you need an x value and a y value. And then for the local min, we need to find f of 4. Well, this is equal to, this is a little easier because it's not a fraction. And when you find f of 4, you get negative 48. So this is 4, comma, negative 48. That would be your local min. So again, you are just plugging all this into your calculator. Just you can watch the signs, right? The exponents, definitely with the fractions. Use the ABC button for the fraction, okay? And that's how you find the intervals of decreasing and increasing, your extrema and critical points. So let's do a few more, especially those fraction ones. So we go to the second one. Again, this is just coming from that handout, right? Right here, this found on Canvas. It'll be linked right next to the video or on the files tab as well. So to find the critical points, what do we do first? You have to take the derivative, right? CP, got to take the derivative and set it to 0. So how are we going to take the derivative right here? Quotient rule. So G times F prime minus F times G prime all over the denominator squared. So what does that equal if we distribute? We get 4x cubed minus 24x minus 4x cubed divided by x squared minus 6 squared, like that. And we set that to 0. If you notice, these get knocked out. So now we have negative 24x over x squared minus 6 squared equals 0. What do you do when you have to solve a rational expression that's been set to 0? You set the top to 0. You set the bottom to 0. This is easy, this one. This is just x equals 0, right? For this one, how do you solve it? You move the 6 over. Then you take the square root of both sides. So now we have x equals, well, square root of 6 is nothing nice, but we're still going to have plus or minus, so it's plus or minus root 6. So in this case, we have 3 critical values or critical points. It's 0, and then positive root 6 and negative root 6, right? Now from here, what are we going to do? We're going to draw our little number line. And we're going to choose test values. So we have 4 regions. 1, 2, 3, and 4. Now, something smaller than negative root 6 to test. Well, negative root 6, you know, is like negative 2 point something, right? So let's just choose something like away from it, like negative 5, for example. Okay. So I'm going to test x equals negative 5 in region 1. You can test negative 10 or negative 18, negative 9,822, because that still lies in region 1. That does not matter, because ultimately what we're looking for is what's the sign of this going to be when we plug it into the derivative? Is it going to be positive or negative? All right. So if I test negative 5, what happens right here? Remember, I don't care what the value of the number is. I just care about the signs. So what's a negative 24 times a negative 5? Well, I know a negative times a negative is a positive. And the denominator, what's going to happen? You're always going to have a positive. Why? Because it doesn't matter if this inside piece is negative, because what's a negative squared? Positive. What if the inside piece was positive? What's a positive squared? Positive. What's a positive over a positive? Positive. So you know you're increasing in the first region. Now let's choose something between 0 and negative root 6. Remember, negative root 6 is like negative 2 point something. Let's just test x equals negative 1. It's the easiest number, right? So we have negative 24 times negative 1 over negative 1 squared minus 6 squared. Again, negative times a negative is a positive. The bottom's always going to be positive right here because that's square on the outside. So you have positive right here. Now, what about the next piece right here? 0 to root 6. We have x equals 1. Just use that. So we have negative 24 times 1 over 1 squared minus 6. And that quantity squared. Negative times a positive is a negative. The bottom's always going to be positive, right? Regardless, because of that square right here. Squaring anything makes it positive. What's a negative divided by a positive? A negative. Then something bigger than 6. I'll test x equals 3 for the fourth region. So we have negative 24 times 3 over 3 squared minus 6, and all that stuff squared. So positive is a negative. The bottom's always positive. What's a negative divided by a positive? A negative. Okay. Remember, we're doing this to help us determine where stuff's increasing and decreasing from. So now we have all that, right? So remember, it's increasing where we have the plus signs, right? Where do we have the plus signs? Here and here. Well, you may be tempted to go, oh, it's increasing from x equals negative infinity to 0, right? Because you got plus and plus right here. But there's a problem. It's this negative root 6. We can't use this because this says we can include negative root 6. But what happens if I plug negative root 6 into the derivative or into the function? You get 0 in the bottom. So 0 in the bottom makes it undefined. So you have to be careful, okay? Because when you have values that make the function undefined, you have to stop at those particular values, meaning I have to go from negative infinity to negative root 6, and then negative root 6 to 0. So be very careful with that. So these in the purple make the expression undefined. There's still critical points, but as far as the interval notation, you have to be careful with those, okay? So we have to stop at it briefly and then start back up again. If you say, again, from negative infinity to 0, you're saying it's legal to plug in negative root 6. But again, we can't plug that in because that'll make the bottom undefined right there. Now, where are we decreasing from? Well, starting at x equals 0 to same issue, right? I can't say 0 to positive infinity. I can't do that, right? Because then you're including root 6. We can't put root 6 in because you'll get undefined. So we have to stop at root 6 and then pick up again at root 6 and go towards x equals infinity. So that's where it's increasing and decreasing from. Now, what about the local max or min? So remember, local maxes or mins happen where you have sign changes from positive to negative, negative to positive. Well, we have plus plus, so nothing's happening there. Minus minus, nothing's happening there. Well, look at this point right here, right? Plus minus. What does that mean? Remember, it means, oh, as I approach 0 from the right, we're going up. And then once I cross zero, I go back down because my slope's negative. So if you have a hump that's opening down, you have a local max. So at x equals 0. But we need to find f of 0, correct? So y is equal to f of 0. What is that? So remember, we're going to take this and plug it back into the original function, not the derivative, okay? Basically, you wind up with 0 over -6, which is 0. So your answer is 0, 0. Do we have a local min? Well, do you have a spot where it transitions from negative to positive anywhere? No, so none. Okay, that's completely possible. All right, so I'm gonna go to 4. I'll let you try number 3 on your own since it does involve the quotient rule. Four is the natural log problem. All right, so to find those critical points, right, have to take the derivative and set it to 0. What's the derivative of ln of x squared plus 3? Remember, derivative of ln of stuff is 1 over the stuff times the derivative of the stuff. So it's basically 2x over x squared plus 3 equals 0. Got a fraction again. What do? We set the denominator to 0, ups the numerator and the denominator to 0. So this is x equals 0. How do you solve this one? Well, you bring the 3 over, right? We get this. Then we take the square root of both sides. So we get x equals, this one's a little different, right? What's the square root of -3? Well, first of all, you're going to have 2 answers, plus or minus. And remember, the square roots of negatives are imaginary. So you have this. Now, we encountered this, I believe, in 4.1. If you have imaginary solutions, they can't be used as critical values. So you ignore imaginary solutions as, I'll say, critical values. Why? Because remember, critical values have to be real numbers. Imaginary numbers are not real. So this makes the problem a lot easier, right? Why? Because we only have one value to work with right here. Well, one value to test around 0. So you only have 2 regions, 1 and 2. Okay. So let's do this. Let's test x equals -1. Keep it easy, right? Or are you going to plug that in to your derivative right here? So if I do that, we get 2 times -1 over -1 squared plus 3. Again, you just care about the signs. 2 times -1 is negative. That's a negative number. And then -1 squared is positive, plus positive is positive. What's a negative over a positive? It's a negative. So we know we're decreasing to the left of 0. What about to the right of 0? I'll just test x equals 1. So if I plug that in, remember, we're going to take that and plug it into the derivative. And as you can see right here, we get positive over positive, which is positive. So we got that, right? So where are we increasing from? Well, starting at x equals 0. And forever to the right, we are going towards positive infinity. Where are you decreasing from? Well, you're decreasing beginning at x equals -infinity. Until what x value? 0. Do we have a local max? Well, what's happening with this minus plus? If we were to draw the humps, remember, negative means negative slope, so you're going down. When you hit 0, what happens? It transitions into positive. So you have a hump that's opening down. Is that a local max or min? Well, it's got to be a local min, right? So this is a local min at x equals 0. Do we have a hump opening up anywhere? No. So there's no local max. Remember, we got to find the y value for this. So we need to find f of 0. What is f of 0 in this case? Remember, you need to go back to the original function. So that is ln of, and we're going to have 0 squared, right, plus 3. That equals ln of 3. So your local min is at the point 0 comma natural log of 3. Don't convert this to a decimal unless the problem asks you, and it's probably not, so leave it in exact form. So again, important with this problem that came about, it was a lot shorter, but the reason why is because when we solve for x, remember the denominator, we wound up with imaginary solutions. If you get imaginary solutions, they cannot count as critical points. You just ignore them, okay? Let's try number 5. Five says 4x to the 2/7. Okay, critical points. What do we do? Take that derivative, right? And set it to 0. So how do you do that? It's the power rule. So you're going to have 4 times 2/7. That is 8/7 x to the negative 5/7, right? Remember, you have to subtract 1. 2/7 minus 1 is negative 5/7. This is the same thing as saying 8/7 x to the positive 5/7 equals 0. So you have a fraction, right? Rational expression. What do? We set the top and bottom to 0, but there's no x up top. So you don't say 8 equals 0 because there's nothing to solve for. The bottom we can solve for, right? This. But what does x have to be right here? Don't go, what do I do with the 5/7? I mean, you could sit here and divide by 7, and do this, but you still get 0. Then how would you get rid of the 5/7? You would raise everything to the 7/5. But what's 0 to the 7/5? It's just 0, right? So that's a critical value. That's the only critical value. So again, just 2 regions like the last one. Now, you're going to plug in a number less than 0 and bigger than 0 into the derivative, and you want to see what the signs are. If I test x equals -1, for example, we get 8/7 and then -1 to the 5/7. Well, it's a positive over a negative, which is a negative. What about x equals +1, something in region 2? Well, that's 8/7, 1 to the 5/7. That's just positive over positive, which is positive. So we have that now. Where is it increasing from? Well, we got a plus sign, right? Starting at x equals 0 to x equals positive infinity. Because remember, this is positive forever to the right. And then where's it decreasing from? Smallest x value is negative infinity. So starting at x equals negative infinity to 0, right? Because that's where you have the minus signs, you're decreasing. Local max or min. Well, look at this hump, right? Negative to positive. What does that mean? It's going like this. We don't have an upward hump, a hump opening up, so there's no max, no local max. But there's a local min right at x equals 0. Now, what do you do to find the y value? F of 0 is just plugging the 0 into here. What's 4 times 0? It's just 0. So your answer is just 0, 0 as a point. Now let's do the last one, the trig one. So again, critical values, what do? You got to find that derivative and set it to 0. What's the derivative of this equation? 1. What's the derivative of cosine? It's negative sine. So we're going to have minus 2 sine of x equals 0. If we solve this for sine, right, we get sine of x equals 1/2. So remember, we're bounded between this region 0 to 2 pi. Okay. That's important for when we find these solutions right here. So where does sine of x equal 1/2? It equals it in 2 places, right? Remember, we have our little unit circle. You have it right here and here. This is, remember, square root of 3 over 2, comma 1/2. This is negative square root of 3 over 2, comma positive 1/2. So remember, sines are the y values, cosines are the x values. If you forgot that, go look at the trig review on Canvas, right? There's the videos, Paul's online notes. Look at that, look at the trig, go over that unit circle stuff, okay? So there's 2 places. So it's equal to, sine of x is equal to 1/2 when x equals pi over 6. That's here, and 5 pi over 6. So those are your critical values. Now we need to draw our line and do our testing, right? And this time we're trapped between 0 and 2 pi. So 0, pi over 6, 5 pi over 6, and then 2 pi. So what can we test? Something in between 0 and pi over 6. In that first region, you can do pi over 12. That's small. Something nice between pi over 6 and 5 pi over 6. Pi over 2, that works. What about between 5 pi over 6 and 2 pi? How about 3 pi over 2? Because that's also a nice value on the unit circle. So what are we going to do with these values? Plug them into the derivative and see if we wind up with a positive or negative number. So if we plug pi over 12 in, we get 1 minus 2 sine of pi over 12. So sine of pi over 12 is not a nice number, okay? So what you're going to do is you can plug it in, you'll get a decimal, okay, into this thing. But before you do that, though, you have to make sure you're in the right mode. Remember, you have radians and degrees. To check if you're in the right mode, press the degree button right here next to the second, DRG. Make sure you're in radians. If you're not, like say if you saw this, just tap it over, tap the right cursor over and go to radian and hit enter. And then we just type it in, 1 minus 2 sine of pi over 12, and just hit enter. So we got 0.4823. Okay, we don't care that it's 0.4823, whatever. All we care about is that it's positive. That's all that we care about. That just tells us, oh, it's increasing from 0 to pi over 6. What about between pi over 6 and 5 pi over 6? We're going to test pi over 2. So we have 1 minus 2 sine of pi over 2. This one, we don't even need a calculator, right? Because what's sine of pi over 2? It's 1, right? So we have 1 minus 2 times 1. That gives you a negative 1. That's negative. So we know we're decreasing between pi over 6 and 5 pi over 6. What about between 5 pi over 6 and 2 pi? Well, we're going to test 3 pi over 2 because that's a nice value. That's 1 minus 2 sine of 3 pi over 2. What's sine of 3 pi over 2? That's negative 1. So you get 1 minus 2 times negative 1. Well, this is 1 plus 2, which is 3, right? That's positive right there. If you want, you can throw all those, the pi over 2 one and the 3 pi over 2 one, into the calculator, just like what we did right here. and it's going to spit out these values. But again, make sure you're in the right mode. You have to be in radian. Again, to check, you press the degree button, DRG, and make sure rad is highlighted for radians. If you do it with degree, you're going to get something completely screwed up or the incorrect answer. So we have that, right? Now we can figure out, where is this thing increasing from? Increasing, decreasing. So where are we increasing? Well, we have the plus signs. Remember, we're bounded between 0 and 2 pi. So starting at x equals 0, 2 pi over 6, we're increasing. We're also increasing from 5 pi over 6 to 2 pi. Because again, we have the positive region right there. Where are we decreasing from? Well, we have the minus signs. What is that from? Pi over 6 to 5 pi over 6. Okay, we got that. What about local max or min? Do they exist? Well, again, what's happening right here? When you go from a positive slope to a negative slope, you're going up the hill. Then once you cross pi over 6, you start to go down the hill. Right here, we're going down the hill. We get closer to 5 pi over 6. And then we go up the hill as we cross pi over 6. So we have a hump opening up and down. So we have both, right? Remember, this opening up is a local max. Opening down is a local min. So local max at x equals pi over 6. So remember, we need the y value, right? How are we going to figure that out? Y is equal to f of pi over 6. So we're going to plug that pi over 6 back into the original expression. So we have pi over 6 plus 2 cosine of pi over 6. So this is y equals pi over 6 plus 2. And what's cosine of pi over 6? That's the square root of 3 over 2. Again, it's important that you know what the unit circles and the values. If you forgot that, go look at that review. So what happens right here? This is just pi over 6 plus root 3 because the 2's can cancel. So as an answer, you'd have pi over 6 comma pi over 6 plus root 3. This is your x value. This whole thing here is your y value. Don't convert that to a decimal unless the problem asks you that. It probably won't, so leave it in exact form. This is your local max. The local min, that happened at x equals 5 pi over 6. So how do we figure out the y value? We got to find f of 5 pi over 6. What is that? That's 5 pi over 6 plus 2 cosine of 5 pi over 6. And then what do we get right there? You get 5 pi over 6 plus 2. What's cosine of 5 pi over 6? It's negative square root of 3 over 2. And the 2's cancel. So you get 5 pi over 6 minus square root of 3. So your answer as a local min is 5 pi over 6 comma 5 pi over 6 minus square root of 3. Again, leave it as an exact form. No decimals unless it asks you for them. So we're going to stop here. This is the first part of 4.3. The next part is concavity and inflection points will be posted in the next lecture.